Good morning, friends. In this chapter up to that, we discuss about reflection, and also reflection uh, by the lens and also the prism. Okay. Now, after that, the one more the phenomena of light is that the scattering of light. Scattering of light, that means there is a quite different than the phenomena of the reflection and refraction. In reflection phenomena, when the ray of light is traveling from one medium to the another medium, at the time the direction of its motion or the traveling is going to change. Now here in scattering phenomena, what's happened? We know that the atmosphere is surrounding the earth. That means around the earth, the atmosphere is present. In an atmosphere, the water particles, dust particles are present. When the sunlight is traveling through such atmosphere of the earth, at the time what's happened? This particle first absorb the incident light on it, and then that is the re-emitted in all direction. Re-emitted this light in all direction. And due to that result, in our daily occurrence, we see the object with the colorful or the color. Some objects are shown the black, some objects are shown the reddish, bluish, white. Okay. So that is due to the phenomena of the scattering. Again, when the sunlight passing through the atmosphere of the earth, so atmospheric particle first absorb this light and then re-emitted in all direction. What is the proportion of radiation of this energy of the light? That is depends on 1 upon lambda is to 4. Okay, we discuss this thing. When the sunlight travels through the atmosphere of the earth, its direction changes by the atmospheric particle. This phenomena is known as the scattering of light. Here also, the direction of the sunlight traveling through the atmosphere is continuously changing due to the atmospheric particle. And this phenomena is known as the scattering. The light of the shorter wavelength, we know that the white light, that means the sunlight, is made up of 7 colors, red to violet. Now, the light of the shorter wavelength is scattered more than the light of longer wavelength. Light of longer wavelength. Actually, the violet and blue light has the shorter wavelength compared to the other, that means the red light. Therefore, the scattering of the blue light takes place first, then the red light. Actually, the scattering of the violet light is first, but our eye are sensitive about the bluish color or the blue color. And due to that reason, we know or we see the sky is on the bluish instead of the violet. Okay, now the light of the shorter wavelength is scattered much more than the light of longer wavelength. The amount of the scattering is inversely proportional to the fourth power of wavelength. So how much amount of incident light is scattered? That is depends on the wavelength of the incident light. That means the amount of the scattering is inversely proportional to the fourth power of wavelength of the light, and that is known as the Rayleigh scattering. And according to that, the scattering intensity or the scattering amount is proportional to the 1 upon lambda is to 4. So sometimes the objective question may be asked from that. The wavelength of incident light is given. Find the Rayleigh scattering, or how much amount of scattering take place of incident light. Here the wavelength given. Therefore, the amount of the scattering is proportional to the 1 upon lambda is to 4. Clear this? Okay. Now, after that, the intensity of the scattered light depends on the ratio of the size of the particle and wavelength of light, incident light. Just we discussed that the scattering phenomena take place when the sunlight traveling through the atmosphere of the earth. So in the atmosphere of the earth here, the dust particle and also the water particle are present with a different size. Therefore, the intensity of the scattered light depends on the ratio of the size of the particle and wavelength of the light. That means that it depends upon A upon lambda. What is say? A is size of a particle, while the lambda is wavelength of a light. Therefore, this ratio is denoted as alpha is equal to A upon lambda. A upon lambda. Clear this? Okay. Now, again, the LS scattering is depends on wavelength. That means is proportional to 1 upon lambda raised to 4. While the intensity of the scattered light, whatever the light is scattered by the particle, what is the intensity of this light? That is depends on A and lambda, ratio of A and lambda. Now, on the base of the side of the scattered particle, here are the three types of the scattering phenomena. First is if on the pole A less than lambda, scattering is known as the Rayleigh scattering. If the size of the particle is very small, then compared to the wavelength of incident light. So such scattering is known as Rayleigh scattering, which is proportional to the 1 upon lambda raised to 4. There is 1 upon lambda raised to 4. So objective question may be asked from this: for which of the following case the scattering is Rayleigh scattering? For this case is given, the scattering is known as blank. So there is the Rayleigh scattering, and there is proportional to the 1 upon lambda raised to 4. Now, second case is that if dimension of a or the size of a scattered particle is much greater than the wavelength of incident light, that is known as geometric scattering. Sometimes in atmosphere, the dust particle and water particle has the size is much more than the wavelength of incident light. At that time, the scattering occurs, but this scattering is known as the mean scattering. It's known as mean scattering. So here, condition is this. If the size of a particle is very large compared to the wavelength, so such scattering is known as geometric scattering. Okay. If the A is equal to lambda, then it is called the mean scattering. That means the size of the scattered particle is same as very close to the wavelength of incident light. So such scattering is known as the mean scattering. Therefore, the three types of the scattering, that is depends on the size of a scattered particle. Clear this thing? So there is the phenomena of scattering and types of the scattering, and what is the Rayleigh scattering, and what is the intensity of the scattered light is depends. Intensity of the scattered light is depends on the ratio of the size of the particle to the wavelength of incident light. Okay. On the base of the scattering phenomena, some natural occurrence shown in our life is that why the sky is shown the bluish during the daytime, and also during the sunrise and sunset the sun is shown the reddish, but the cloud in the sky during the daytime are shown the white. What is the reason? So here first we discuss about that why the sky is shown the bluish. Now we know that the blue light or the blue has the shorter wavelength. Therefore, this blue light is scattered much more than other color, and also scattered strongly. Thus, the bluish color predominates in a clear sky. Actually, the violet light has the minimum wavelength or the shorter wavelength. So, violet light is scattered much more and also strongly, but our eye are more sensitive about the bluish or the blue color than the violet. Therefore, we feel that the sky is shown the bluish. The reason is that again the blue has the shorter wavelength than red color and is scattered much more strongly, and bluish color is predominates in clear sky. Therefore, sky is shown the bluish. Sky is shown the bluish. Clear this? Okay. Now we are going to discuss about that. Why at the time of the sunrise and sunset, the sun or the moon are shown the reddish, and also the clouds are shown the white during the daytime. Clear? Okay. Okay, after the discussion of why the sky is shown the bluish, so other natural occurrence like that during the sunrise or the sunset, the sun is shown the reddish, yellow or the reddish. At the same time, what are the clouds in the sky are shown the white. What is the reason? So for that purpose, the scattering phenomena is responsible. Here already we discussed about that, the three types of the scattering, reddish scattering, after that the geometric scattering and mist scattering. Okay, now here, what's happened? Figure shows the sunrise. When the sun rises at that time, what is the situation that is shown in the figure? There is the earth, up to the certain region, the atmosphere is surrounding the earth. So during the morning or the evening time, when the sunlight is coming from the sun, traveling quite more distance in the atmosphere of the earth compared to the noon. Because at the noon, what are the light or the sunlight are incident normally on the surface of the earth. Therefore, here the distance is short. Here quite more distance it has to travel. Now, when the sunlight enters in the atmosphere of the earth, at the time, here in atmosphere the dust particle, water particles are present and the scattering phenomena occurs. Now already we know that in sunlight the blue, violet, red, all the colors wavelengths are included. So this sunlight is scattered by the particle of the atmosphere. This sunlight is scattered by the particle of the atmosphere. Therefore, the blue and violet light, that means the light with the shorter wavelength is scattered first and also the strongly scattered compared to the light with longer wavelength. So when this sunlight reaches to the observer on the surface of the earth, the most of the light with the shorter wavelength, that means the blue color, is scattered. And as a result, there is shown in the sky, that means the sky is shown is bluish. While the non-scattered light, that means the light with the larger wavelength is entered to the eye of a person. Here the remaining wavelengths are yellow, red, orange, this color. Therefore, we feel that the sun is reddish, yellow or the red during the sunrise, and same phenomena occurs during the sunset. And the same way, when the moon rises and moon set, at the same phenomena occurs. While during the daytime, what's happened? Here, what are the sunlight coming from the sun tell the less distance in the atmosphere, and the scattering phenomena take place also during the daytime. But here the scattering take place perpendicular to the incident light. Therefore, blue color are spread in just side. In just side. Okay. Now there is the reason why the sun looks reddish at the time of sunrise to the sunset. Clear? Okay. Only the reason is that the shorter wavelength is scattered fast and strongly compared to the longer wavelength. Therefore, when the sunlight reaches to the eye of a person, at this time the blue color or the color with the shorter wavelength are scattered fast and strongly, and therefore the sky is shown the bluish and only the light with the longer wavelength entered the eye of the person, like as the red or the yellow color. So we feel that the sun is reddish yellow. Okay. Now, what is the next? Why the clouds are seen to be white during the daytime? Now we know that the scattering is proportional to the 1 upon lambda is to 4. But here in cloud, which particles are present? Generally the water drops, ice particle, dust particle with the larger size compared to the nominal particles. And due to that reason, here in cloud, the scattering does not occur with 1 upon lambda is to 4 power. Because here the size of the scattered particle are larger, therefore all the wavelengths are scattered equally. All the wavelengths are scattered equally in a cloud. Therefore, no any particular color are shown. Because all the wavelengths are scattered equally, therefore the clouds are shown the white. And this type of the scattering is known as the diffused scattering. That is known as the diffused scattering. Again, in a cloud, what's happened? The particles, large particle, that means the water particles or the dust or the ice particle. The size of this particle is very large compared to the wavelength of incident light. So here in clouds, the scattering is not proportional to the 1 upon lambda is to 4. Because the A is much greater than lambda. Therefore, in cloud, all the wavelengths are scattered equally. All the wavelengths are scattered equally, therefore no color occurrence takes place for the sun. And therefore, the clouds are shown the white. And here, that is due to the diffuse scattering. Diffuse scattering. Clear this? Okay. And due to that reason, what is which scattering is responsible for the clouds shown the white? So here the diffuse scattering takes place. So this type of the objective question may be asked from this topic of the scattering. Okay. Okay, now last portion of this chapter, there is the optical instrument. Now, what are the optical instruments? There is the design and the base of the lens or the mirror. We are going to discuss about that. The first and simple optical instrument is our simple microscope. Right? Simple microscope, that means our convex lens, that means the conversing lens with the shorter focal length. Or the conversing lens or the convex lens with shorter focal length, that is our simple microscope. For this simple microscope, we want to obtain the equation of magnification. In which case, if the image is not formed at infinite distance, Already we discussed that. In which case, the image is formed at infinite distance. If and only we place the object on principal focus, so its image is formed at infinite distance. But as we place the image between the principal focus and optical center of a lens, or in case of a mirror, the pole and principal focus of a mirror, so its virtual image is obtained in the same size. Image is virtual, react, and also the magnified image is obtained. We are using this concept in simple microscope to enlarge or to magnify the object. For that purpose, question is that define what is the simple microscope. Obtain the equation of magnification for the image focused at normal vision distance. Normal vision distance, that means we can see the object with comfort and without stress of our eye. Now we know that when we read the textbook or the book, at the time we keep the distance of the book from our eye at certain distance, not very close or at far distance. So the place or the point at which we keep the book, so we can easily read without with comfort and without stress. So that is known as, this distance is known as normal vision distance or the near point distance. Okay. A simple microscope is conversing with a convex lens of small focal length. So convex lens is act as a simple microscope. Therefore, simple microscope is a conversing or convex lens with small focal length. To use the such lens as a microscope, the lens is held near the object, very close to the object. Either the object is on focal length or the focal point, or more distance or less than the focal point distance. And eye is kept very close to the lens on other side. Now here there is the convex lens. Here, in case of a convex lens, the object is placed. That is the principal focus F. So object is placed at either focal length or less distance or away distance from the principal focus. So its image is for, and we keep the eye at other side of this lens to obtain the image. Therefore, here magnified and virtual image of the object is obtained. So yes, we are observing the object from the other side of the lens, we obtain the real magnified and virtual image of this object. Now, so that it can be seen comfortably. So, if the object is placed between the optical center and principal focus, at that time its image is obtained at the same side. And this image is virtual, yet and magnified image is obtained. And this image is formed at the comfort distance. That means approximate D is equal to 25 centimeter. D is at 25 centimeter. Now, if the object is at principal focus, so its image is formed at infinite distance. Again, the image is formed at comfort distance if and only if the object is placed between the optical center and principal focus of a lens. If the object is placed on principal focus, so its image is formed at infinite distance. Okay. Now, so what is the figure of this discussion? So figure is that here the convex lens or the conversing lens with the small focal length, that is the principal axis, that is the object is placed at a point on the principal axis between the optical center and principal focus. Principal focus that is here. Therefore, the image of this object is formed in the same side. Also, the react, virtual and magnified image is obtained. Okay. If the object is at a distance less than the F focal length, the image of virtual closer than the infinite, that means the image is not formed at infinite, but it is formed at normal distance D is equal to 25 centimeters. Now, in this case, we want to obtain the equation of magnification. We know that the magnitude of magnification M is equal to ratio of image distance to the object distance V upon U. Now, we are using the equation of lens for the lens formula minus 1 upon U plus 1 upon V is equal to 1 upon F. From this equation, 1 upon U is equal to 1 upon V minus 1 upon F. 1 upon F taken this side, 1 upon U taken on R axis. Therefore, 1 upon U becomes positive is equal to 1 upon V minus 1 upon F. Now, multiplying by V, that means the image distance on both sides. Therefore, V upon U is equal to V upon V minus V upon F. V upon V is 1. And we know that the magnification M is equal to V upon U. Using this concept, therefore M is equal to 1 minus V upon F. Now, in figure, our image is formed at V distance, that means the V. Now, according to the sign convention, the V is measured in opposite direction of incident light. Therefore, V is equal to D, but that is negative. Therefore, we are substituting the V as minus D. Therefore, M is equal to 1 minus. Instead of the V, I place minus D. So, minus D upon M. Therefore, M is equal to 1 plus dm. 1 plus dm. That is the magnification of a simple microscope, in which case, if the image is formed at near point distance or the normal vision distance. Clear this? And also we are going to obtain the magnification of a simple microscope if the object is placed at principal focus. At that time the image is provided in finite distance in next portion. Clear?